sometimes choosing orders of integration, starting with x or starting with y, can make it more convenient. Other times, it takes it from impossible to possible, and that's what we want to look at here. So supposing I have this function, and it's bounded, so that there's a function that's bounded by e to the negative x squared, and that's going to be above, because e to the negative x squared looks like what you think of when you think of a bell curve. It's pretty close to that. And then z equals 0 is the xy plane. Y equals 0 is this red plane here. So it's the xz plane. X equals y is this green, very terribly drawn plane here. And x equals 1 is the orange plane. So you have all these slices and dices. Everything that comes up from here is cut, so that you end up with this little triangular region that goes straight up, but then that cuts into this function, which I didn't dare try to draw there. But the idea here is we want to find the limits of integration, and we want to solve this thing. So if we were going to solve this thing naively, we might take one method where, I'm going to use my cheat sheet here. We might use a method where we wanted to integrate with respect to x first. So if I'm trying to integrate with respect to x, it looks like the x values go from 0 on the x to wherever y is. So x, it always goes from 0 to y. Actually, no, that can't be right. It goes from y to 1, right? It has to go from y, whatever y is, all the way to 1. So my notes have to be wrong, but that's okay. No, my notes aren't wrong. I just didn't read them correctly. Read your notes correctly. So in this particular case, then y would go from 0. Y goes from 0 to at maximum 1. And x goes from, my goodness, from whatever y is to 1. Right? Because x starts at whatever y's value is and walks its way to 1. All right. Well, I've set up this integral. Good, great, grand, wonderful. Now, what do I do with it? Well, the problem is you're going to be here all day integrating that. So if I was just trying to do this integral, you can go look it up. There's no table for it. There's nothing. In fact, if you look it up, I believe you'll get ERF x, which stands for this error function of x. And you'll find that what this thing says, it says e to the negative x squared has no elementary antiderivative. What does that mean? Well, what that means is I could get like a Taylor series of this thing, and then I could integrate the Taylor series, and I'd have some sort of infinite sum. But that's not, we wouldn't call that an elementary antiderivative, because it's not the sum of what we think of as elementary functions. So this is a problem. Basically, it's not possible to do. So why don't we try changing the limits of integration here? So instead of saying, okay, x goes from y to 1, well, let's look at what y or what x does. Let's say x goes from 0 to 1. And then for whatever x is, y goes from 0 to whatever x is. Y goes from 0 to x. See, this time I got it right. I looked to check. Didn't have to. But because this is a constant relative to dy, it doesn't actually matter. We can just cheap out on it. We can say, okay, well, that's just e to the negative x squared y from 0 to x dx. Well, when y is 0, it goes away. When y is x, I end up with 0 to 1 x e to the negative x squared dx. Then I can let u equal negative x squared du equals negative 2x dx. Or I can say negative 1/2 du equals x dx, because I have an x dx. So then I get, when x is 0, u is 0. When x is 1, u is negative 1. So negative 1/2 e to the u du gets me negative 1/2 e to the u from 0 to negative 1, which is negative 1/2 e to the negative 1 minus 1, or 1 minus e to the negative 1 over 2, which is the answer I wrote down, thank goodness. But the idea here is that choosing the order was the difference between unsolvable and solvable. Maybe not super pretty, but still solvable nonetheless. So if you're having issues with one order of integration, try swapping it. You might find that integration is much, much smoother.